Okay. Okay, so I think everything is set up. So folks have figured out how to record and broadcast this live. So I'm just saying that in the future, if you can't make it to class, you can still join us. And if you miss the class entirely, you can still access the recordings, which I'll post in Canvas. Okay, so what am I doing here? Okay, so if I remember correctly, the last time we were here, we discussed, I think we completed discussing the scientific method. So I'm just going to move on to the next topic, which is dealing with scientific measurement, right? So of course, in the practice of science, more than likely, you have to take measurements in order to do your work. And basically, it has been agreed upon internationally that the metric system is what is used when it comes to making scientific measurements, right? So what you're looking at here are the 7 base SI units. SI stands for International System of Units, which is directly related to the metric system, right? So you have the unit of length being meter, according to the system. The unit of mass is kilograms. For time, it's seconds. For temperature, it's Kelvin. For the amount of substance, it's mole. And for the electric current, it's ampere. And luminous intensity, the unit would be candela, right? So these are the units used by scientists all over. And the last two, we will not be using in this course. For those of you who have to do general chemistry too, there is a chapter dealing with electrochemistry, and therefore you will encounter the ampere unit when you get to that chapter, all right? So, along with the base units, you need to use what are known as metric prefixes to express larger or smaller values, all right? And of course, that is necessary because, of course, in science, when it comes to measuring pretty much anything, you can have, medium numbers or medium-sized numbers, but you can have numbers that are very small and numbers that are very large. So therefore, the use of prefixes becomes useful when it comes to those measurements that are extreme in terms of magnitude. So this here is a small sample of the different prefixes. The more comprehensive ones will be provided or is provided in the packet that I showed you guys that is posted in Canvas, right? So just to highlight a couple of them. So 10 to the 9, that's Geiger, all right? 10 to the 6, that's mega. 10 to the 3, that's kilo. And then for the smaller units, 10 to the minus 6 is micro, 10 to the minus 9 is nano, and so on and so forth, all right? So whenever you're using the metric system, it's very important that you understand what these different prefixes mean. So for example, okay, so for example, if I were to write down 29 millimeters, right? Now the prefix milli, which is right here, means 10 to the minus 3. So therefore we can equate this to 10 to the minus 3 meters. Let's see if I can use a different color. Okay, so because milli means 10 to the minus 3, that means that 1 millimeter is equal to 10 to the minus 3 meters, all right? Just to give another example, using a larger prefix value. So if you're given 55 kilograms, right? Well, the prefix kilo, if you look it up here, is 10 to the 3, right? So that means that 55 kilograms would be the same thing as 55. Oh, by the way, this should be 29 times 10 to the minus 3, my fault. And this here will be 55 times 10 to the 3 grams, all right? So that's basically how you interpret the prefixes, all right? And you'll be using this a lot, of course, in your future calculations. And I'm quite sure you're familiar with them anyway from your introductory or high school chemistry. So what we're gonna do now is look at the different types of measurements, and the first one we're gonna look at is length, and we're gonna look at the related type of measurement, which is area. The base unit of length according to the SI system is a meter unit, which is slightly longer than a yard. I think 1 meter is equal to, do I have it here? No, I don't have it here. I think 1 meter is equal to 1.0936 yards or something like that, all right? So that's the base unit of length. And then we have some derived units based on, of course, the use of prefixes along with that base unit. So kilometer, kilo means 1,000, so 1 kilometer is equal to 1,000 meters. And just to give an idea how a kilometer relates to a mile, 1 kilometer is about 2/3 of a mile. Centimeter, centi, the prefix means 10 to the minus 2. So 10 to the minus 2 meters is equal to 1 centimeter, which is the same thing as 0.01 meters. And then milli, that prefix means 10 to the minus 3. So basically 1 millimeter is equal to 10 to the minus 3 meters, and so on and so forth. Then we have the derived unit of area, right? Area is related to, well, depending on the shape of the what do you call it, the plane where the area is covering. There's a relationship that you can establish between the length and the area. As a result of that relationship, we can express the area as some unit of length squared, right? So for example, just as how you have the unit of length being meters, you can also have the unit of area being expressed as meters squared, for example, right? And we can see how that is derived, because if you have a square, a perfect square, right, where each length is 1 meter, 1 meter here, and 1 meter here along each edge, that means that the area, according to the definition of the area of a square, would be 1 meter times 1 meter, which would be equal to 1 meter squared. All right, so that's where we get the unit of area being equal to the unit of some unit of length squared. All right. Okay. Then we get to another derived unit for volume, right? Now, by definition, the volume, and I think I mentioned this earlier, the volume of an object is the amount of space it occupies. All right. And the derived unit of volume can be expressed as a unit of length cubed. So for example, the volume can be expressed in terms of, let's say, meters cubed, or it can be expressed in terms of kilometers cubed, or even if you're going to use non-metric units, it can be expressed as inches cubed or feet cubed. It all depends, all right? Now, there's another unit that is used to express volume, which is not a derived unit. It's not an SI unit per se, but it's a metric unit. It's called the liter unit, right? And you can use, again, prefixes along with that base unit to express larger or smaller unit values, all right? So for example, milliliters, milli means 1,000th or 1/1,000. So therefore 1 milliliter is equal to 1/1,000 liters, or 0.001 liters, right? And it turns out that the milliliter unit can also be expressed in terms of centimeters cubed, right? In fact, 1 milliliter is equal to 1 centimeters cubed, all right? So that's the equivalence between those two units, right? And this box diagram right here kind of illustrates the relationship between the different units. So basically this box, this larger box here, which is a large cube, is made of smaller cubes that are stacked in a particular way, up, across like this, and across like this. And these smaller cubes will have a volume of 1 centimeters cubed. So if you stack them in a way to form a larger cube, you're going to see that you're going to need 1,000 of these cubes in order to make a larger cube here, where the volume would be equal to 1,000 centimeters cubed. All right. So as we said before, we said that 1 centimeter cube is equal to 1 milliliter, right? So that means that 1,000 centimeters cube would be equal to 1,000 milliliters. And because 1 milliliter is 1,000th of a liter. That means that 1,000 milliliters would be equal to 1 liter, which is what we have here, right? 1 liter is equal to 1,000 milliliters, right? So basically, we can write down the relationship between the liter unit, the milliliter unit, and the centimeter cube unit. So I'm just going to write it up here. 1 liter will be equal to 1,000 milliliters, which would be equal to 1,000 centimeters cubed. And then there's another relationship that we can write down with respect to this unit here, decimeters cubed, right? Now, basically, how am I going to say this now? Basically, 1 decimeter is equal to 10 centimeters, all right? That's a relationship between the decimeter unit and the centimeter unit. Now, if you were to cube this and cube this, you're going to end up with 1 decimeter cube, which is a result of cubing this, will be equal to 1,000 centimeters cubed, which is the result of cubing 10 centimeters, right? So basically, 1 decimeter cube would be equal to 1,000 centimeter cubed, which is equal to 1,000 milliliters, which is also equal to 1 liter. So therefore, we can say that 1 decimeter cube is equal to 1 liter. So basically, what I'm just showing you is the different relationships between the different volume units, all right? Okay, any questions so far? Any questions? Any questions? Okay, another measurement, mass. Let's first define what we mean by mass, because in everyday language, people tend to use the terms mass and weight as if they mean the same thing, but technically speaking, they're two different things. Mass is the amount of matter that's in an object, right? While weight is the force that the object will have on a surface due to the pull of gravity on that object, all right? So that's the difference between mass and weight. Now, people confuse the two because they're actually related to each other, right? The greater the mass of the object, the heavier it's going to be, all right? Everything else being the same, right? But they're two different things, all right? And there are different units that we use to express these values. So the base unit of mass is a kilogram unit. And of course, kilo means 1,000. 1,000 kilograms is equal to 1,000 grams is equal to 1 kilogram. All right, and just to give you an idea as to what a kilogram is all about, it says here 1 liter bottle of soft drink weighs about 1 kilogram. All right, and there are some other mass units that are used, like the gram and the milligram units and others as well. So that's basically it as far as mass is concerned. And then when it comes to time, the SI unit of time that is used all over is seconds. But of course, we can have smaller values, which are oftentimes used, or smaller units, which again results from using the prefixes. So for example, you can have the millisecond, nanosecond, microsecond units, depending on what you're trying to measure. And then when it comes to larger units, we tend to use, units such as days or hours. I can't, to be perfectly honest, I can't recall ever seeing anything like kiloseconds, for example, or megaseconds, right? Not that it can't happen or it doesn't exist, but it's not oftentimes used, all right? So when it comes to larger units of time, we tend to use things like years, months, hours, and so on. Okay, the next type of measurement is temperature, right? Now, temperature, of course, is basically a property that tells how heat energy would flow, right? And we're going to learn more about that in chapter 6, all right? Basically, if you have two objects in contact with each other, if one has more heat energy than the other, then the heat will flow from the hotter object to the cooler object, right? And basically, you can tell the direction of the flow based on the temperature differences between the two objects that are in contact with each other, all right? So when it comes to temperature, there are different units. The base unit, according to the SI system, is the Kelvin unit. And this unit is basically used pretty much throughout, definitely in chemistry for the most part, all right? Even though other units can be used as well, such as the Celsius unit, which is also known as the centigrade unit, all right? And the Celsius unit is was basically derived based on the properties of water. What they decided, and I'm not sure who made the decision, but basically what was decided was that the temperature of ice, or the temperature of water at the melting point, I should say, was defined as 0 degrees Celsius, and the temperature of the boiling point temperature of water was defined as 100 degrees Celsius. So based on those two settings, that's how we end up with the Celsius scale, all right? But there's yet another unit that is used, mostly used in meteorology for some reason, and that's the Fahrenheit scale, right? Which is basically, for example, if you watch any weather reports on TV, basically when they're quoting temperatures, they quote it in units of Fahrenheit, all right? Now, there is a relationship between these three units. The first relationship I'm going to talk about is the relationship between the Fahrenheit scale and the Celsius scale. And there's an equation that ties these two units together, and that is this equation right here, right? The temperature in Fahrenheit is equal to 9 degrees Fahrenheit over 5 degrees Celsius times the temperature in Celsius plus 32 degrees Fahrenheit, right? So that is the equation which relates the temperature in Fahrenheit to the temperature in Celsius. And usually what I do, if I want to do a quick calculation in my head concerning converting from Celsius to Fahrenheit, basically what I do is that I take the temperature in Celsius, multiply it by 2, and then add it to 32. And that gives you a rough estimation. Usually you'd have to basically take off 1 or 2 or 3 degrees from that to get the equivalence in Fahrenheit, right? And of course, you can rearrange this equation here to get an expression for the temperature in Celsius, all right? So that's how we relate the Celsius to the Fahrenheit scale in terms of an equation. As far as the Kelvin scale is concerned, there's a relationship between the Kelvin scale and the Celsius scale, which I don't have here, so let me write it down. It is the temperature in Kelvin is equal to 1 Kelvin over 1 degree Celsius multiplied by the temperature in Celsius plus 273 Kelvin, all right? So basically, if you want to convert from Celsius to Kelvin, you add 273 to the Celsius value, and that gives you the equivalent value in Kelvin, all right? So that's basically how that is done, all right? Okay, so let's see what's next. Oh, so here's a question. This question says, at home, you like to keep the thermostat at 72 degrees Fahrenheit. While traveling in Canada, you'll find that the room thermostat is calibrated in degrees Celsius. And by the way, that I believe this to be true because pretty much United States is the only country that basically expresses temperature, like in weather reports and so on, in degrees Fahrenheit. If you go to pretty much any other country, they express the temperature in Celsius. So it would not surprise me if you go to a hotel room in Canada, you'll see that the thermostat is basically calibrated in Celsius degree Celsius. So the question is asking, to what Celsius temperature would you need to set the thermostat to get the same temperature you'd enjoy at home? So basically, you're going to use this, the equation I showed you earlier, which is T Fahrenheit is equal to 9 degrees Fahrenheit over 5 degrees Celsius times the temperature in Celsius plus 32 degrees Fahrenheit. Now, let me see here. Oh, so you need to find the temperature in Celsius. Okay, so you need to use the other form of the equation, which is Tc is equal to Tf minus 32 degrees Fahrenheit divided by 9 degrees Fahrenheit divided by 5 degrees Celsius. So we put the number in for Tf, which is 72. So that's 72 degrees Fahrenheit minus 32 degrees Fahrenheit, Fahrenheit, divided by 9 degrees Fahrenheit divided by 5 degrees Celsius. So let's see what that gives. So that's 72, well, the top part is going to be equal to 40 degrees Fahrenheit. and then you're going to divide by 9 degrees Fahrenheit over 5 degrees Celsius. So let's see what I get. 40 divided by, okay, so according to my calculation, this works out to be equal to 22 degrees Celsius. All right, so basically that's the equivalent to the 72 degrees Fahrenheit. All right. Any questions about this one? Any questions about this example? Any questions? Yes, ma'am.
How'd you put it in the calculator with the 40 over the 9 degrees to the 5?
It kind of depends on the calculator. On my calculator, what I would do is divide the 40, and then I'd put open parentheses, and then put 9 divided by 5, and then close parentheses, and then hit the equal sign. That's what, you know, that's the most convenient way for me on my calculator. So you take the 40, divided by open parentheses, 9 divided by 5, closed parentheses, and then equal. And that gives you the answer. Okay, any other questions about this one? Any other questions? All right, let's see what's next. Okay, so now that we have covered the different types of measurements, we're going to talk about some very important aspects of carrying out measurements, and that is involving these two terms, precision and accuracy. And again, this is one of those situations where everyday language, people think that these two terms mean the same thing, but again, technically speaking, they're different. So what do we mean by the term precision? Well, precision basically refers to how closely repeated measurements approach one another, all right? So just to give an example, let's say I gave you guys the task of measuring, let's say, the length of your desk, right? And I gave you the instrument to measure it, which would be a meter stick. So each person independently go and measure the length of the desk, and let's say we record it on the board, let's say, right? So you measure it, you record your value that you see, and then another person measure it and record their value, and we just continue. And then we look at the values, right? Basically, you'd expect that those values will be relatively close to each other, right? Might be different by maybe 0.1 centimeter or so, but you'd expect them to be basically approximately the same, all right? So basically, we would expect, in other words, the measurements to be precise or very precise, all right? Because you'd expect those values to closely agree with each other. Now, accuracy, it means something different. When we're talking about values being, a measured value being accurate, we're talking about how close that value is to the quote-unquote true value. And we put that in parentheses because one could say that, well, we can't absolutely know what the true value is, right? But basically what that means is that we accept a value which is pretty much standard, and therefore we compare any measured value to that standard value, and how close the measured value is to that standard value basically is a reflection of how accurate that measurement is. And just to illustrate the difference between the two, we have this situation here that you can see on the screen where you have a dartboard, and basically you're given 3 attempts to throw the dart at the dartboard, and you have different situations here. So this is basically like an analogy to the act of measuring an object or measuring something, some value. And we're going to see how this relates to the terms accuracy and precision. So the middle part where the red dot is, at the exact middle of that, that represents a true value. So in the case of the first attempt, somebody threw these 3 darts here, and you see that the darts are all over the place in terms of being far from each other, and they're also far from the center as well, right? So this is basically reflecting a situation of low accuracy and low precision, all right? Now, in the next situation where somebody threw the darts and the darts are close to each other, but very far from the center of the dartboard, so that represents a situation where the accuracy is low because it's far from the dartboard, but because they're close to each other, that means that basically or it's analogous to the repeated measure value being close to each other, which basically what that is representing is a situation where the measurements are very precise or high precision associated with the measurement. So that's low accuracy and high precision, all right? The next one, the third one, is where the darts are relatively close to the center, but they're still relatively far from each other. So the accuracy is relatively high, but the precision is low because the darts are far from each other. And then the final one, which is of course the ideal situation, right? Where all the darts are hitting smack in the middle, right? And this is something that we aim for when we're doing any measurements in the lab. And that basically is reflective of a situation where the measurements are, well, basically the same as the true value. And of course, they're close to each other. So that's high accuracy and high precision being represented there. So that's basically what we aim for whenever we're doing any experiments and taking any measurements. We're trying to aim for high accuracy and high precision. So in the real world, we can never know whether or not the measurement that we make, measurement of anything, is accurate. And it's asking the question here, why not? And the main reason why is pretty much because of the human element. You know, in order to establish the accurate value, some measurements would have to take place. But the thing about it is that measurements are at best estimates, all right? You know, there's no such thing as a 100%, well, I shouldn't say that. I'm trying to find the right words to express what I'm trying to, well, let me just leave it at that. Measurements are at best estimates, right? So you cannot be 100% sure that it's 100% accurate, all right? So basically that's the reason why we do repeated measurements, and hopefully we get high precision, and therefore based on that, we can basically imply that, okay, since the measurements are relatively close to each other when done repeatedly, then basically the absolute value would be the same as the measured value that you are trying to make, all right? So now we're going to get into how do we express the level of precision in a measured value. So the way we do that is by determining what we call the number of significant figures or significant digits, all right? Now, when we're talking about significant digits, let me define it. Right here. No, that's not it. Hold on. Okay, I think I have these slides in a different order. Okay, so this is the definition of significant digits, right? It's a number of digits that are known plus one estimated digit that are considered, plus one estimated digit, and that is basically collectively the number of significant digits, right? So if, let's say you're given a question and this number is given to represent some measurement, right? Then based on that, which you're given, you can conclude that the first 5 digits you're certain about. You know them, right? Based on whatever instrument that was used to get this measurement. And then the last digit would be the estimated digit, which is the 3 in this case, right? So basically, collectively, the total number of significant digits expressed here would be 6 significant digits, 5 of which you're certain about, but the last one is an estimated digit, right? And that is the reason why you cannot be absolutely certain, you know, about 100% accuracy of any measurement, because as I said before, any measurement is at best an estimate. And the reason why it's at best an estimate is because the last digit is an estimated digit, all right? So that's basically a limitation. It's an inherent limitation that exists when you're measuring anything. Now, let me go back to the previous slide. What was the previous slide saying? Okay, so what the point you're making here in this slide right here is that whenever you're trying to record or present a measured value, you don't want to claim that the value is more precise than was actually measured. And they gave the example of driving a car, and let's say the car has a volume in the tank of 14.1 gallons, and you drive 273.0 on a fill-up tank. If you divide the 273.0 by the 40.1, you're going to get these values. But you cannot predict based on that basically this would be the level of precision reflected in this value. And that's because this is based on two measured values. So later on, I'm going to clarify this later on, but basically later on, you're going to see how we determine the number of significant digits in a calculated value, but that's later on. But first, I want to talk about how do we, from an instrument directly, how do we determine the number of significant digits? Now remember, the significant digits in a measured value are those digits that you're certain about plus one, which is an estimated digit, which you're not certain about, right? So what we have here are three thermometers, A, B, and C, right? And you have the mercury level moving on to different extents. And you'll notice that in the case of thermometers A and B, the graduation marks are identical, right? And we can tell what each of these marks represents. So we have 20 here, and we have 30 here, right? And we have 10 equal divisions, right? So therefore, we can say that this is 21, this is 22, this represents 23, 24, 25, and so on, all right? So if you're asked to determine what is the temperature reading in the case of this thermometer, you can tell with certainty that it is 21 point something, right? Because the mercury level is above the 21 mark. So the question now becomes, well, what is that digit after 21, right? So that's where the estimation comes in. You have to look at it and make an estimation as to where that mercury level is. So one person could reasonably say, you know what, I think this is 21.1, right? Another person could look at it and just as reasonably say that I think it's 21.2, all right? Now, if I was given a question like this in a test, I would, if somebody gives 21.1, another person gives 21.2, as far as I'm concerned, both persons are just as correct, all right? Because both persons got it right in terms of the digits that you're certain about, but you have to make an estimation of the other digit after the 21, right? In this particular case, it is 21.2. But like I said, if somebody had said 21.1, I would give that person full credit, right? And therefore, these two digits we're certain about, and this digit is an estimated digit, right? So therefore, the total number of significant digits expressed here is 3 significant digits, all right? Now, in this case here, it's the same sort of scale, but the mercury level, let me back up a bit here. The mercury level seems to fall just exactly on the 22 mark, right? So you might be tempted to say that the temperature being registered here is 22 degrees, right? But the level of precision that is expressed here should be the same as expressed here because they have the same kind of scale, right? So it's not enough for you to say 22. You'd have to estimate a digit after the 22. And, you know, by our estimation, it looks like that digit would be 0, right? So therefore, in this case here, the registered temperature would be 22.0, again, expressing your temperature to 3 significant digits, as we did in the case of thermometer A, all right? Okay, so now we get to the third thermometer, thermometer C, and immediately you'll discover and notice that the graduation marks are even are different in that even though you have these here, which is equivalent to these graduation marks here, you have some smaller lines in between, let's say 20 and 21, right? And there are 10 of them in between 20 and 21, which means that each of these lines represent what? 0.1 degrees, right? So that would basically add to the level of precision that would be expressed when we try to record the temperature here. Now, in this particular case, the temperature, the mercury, I should say, is above, what's going on here? Is above the 22 mark, all right? So we know that, and then right above it, I don't know if you guys can see it, but right above the 22 mark, it seems as if the mercury level is just past the 0.1 mark. So we know that the first 3 digits would be 22.1, right? but it's just above that 0.1 mark. So therefore, again, we have to make an estimation, right? It's 22.1 something, right? So the question now is, what is that something? The only thing we can do to get that something is to estimate it. And basically, one could say that that is 21.1. Another person could say it's 21.2. 22.12, all right? Again, if I was grading something like that, both persons would get the same credit because again, you're certain about, in this case, the first 3 digits, but the digit after the third one is an estimated digit, right? So in this particular case, it is 22.11, and therefore, basically, the temperature here is being expressed to 4 sig figs, right? So basically, as you can see, a lot is dependent on the type of instrument that you're using, right? Obviously, in this particular case, the thermometer to the extreme right, thermometer C, will give you a more precise measurement compared to the first two, simply because of how the thermometer is graduated, all right? So that's just an example, and you can apply this to, other instruments as well. Let me just say also that there are instruments nowadays, of course, where you get a digital readout, right? That's even easier to work with in terms of determining the number of sig figs, because all you have to do is assume that whatever you see on the digital screen, that's a number of sig figs, right? And therefore you can assume that the last digit on that display would be the estimated digit, all right? So in the case of a digital readout, like for example, the balances that we use in our lab here, basically you don't have to go through this trouble of estimating, which digit, the estimated digit, the last digit, because basically the instrument does that for you. Okay, any questions about this? Any questions? Any questions? Okay, so let's talk about the rules for determining the number of significant digits. And this is dealing with situations where you're given a number in a problem. In fact, hold on, let me stick with that. I thought there was another slide which is more detailed, but anyway, let's stick with this. Right, so let's say you're given a problem and the problem has some numbers which are measured values, and in order for you to solve the problem and report your answer to the correct number of significant figures, you need to know what the number of significant figures are in the problem itself, right? So these are the rules that you have to follow in order to determine the number of significant digits in a measured value that you're given, right? So the first rule is the easiest one. All non-zero digits are significant. So all digits that you see in a number from 1 through 9 are significant, all right? The next digit is dealing with zeros. In fact, all the rules after that deals with zeros in different situations. So the next rule says a zero is significant when it is between non-zero digits, all right? So if you have, let's say, for example, in this case, 401, right? This zero here is significant because it's sandwiched between the 1 and the 4. And even if you have more than one zero sandwiched between non-zero digits on either side, those zeros will be significant. So for example, 93.006, these two zeros are significant because they're sandwiched between the 3 and the 6. So therefore, the total number of significant digits here would be 5, all right? Okay, the next rule has to do with a situation where you have zeros at the end of a number and there's a decimal point anywhere in that number, all right? So according to this rule, a zero is significant at the end of a number that includes a decimal point. So if you have a decimal point in a number and you have zeros at the end of that number, then those zeros are counted as significant. So for example, 55.000, that would have a total of 5 significant digits because you have 3 zeros here at the end of the number and there's a decimal point here, all right? So therefore, that's rule number 3. If you have zeros at the end of a number and there's a decimal point anywhere in that number, then those zeros are significant. Okay, number 4. Now this is a situation where a zero is not significant, right? It says here a zero is not significant when it is before the first non-zero digit, right? So an example is shown here. If you have zeros, such as this here, you have 3 zeros here before the first non-zero digit, then those zeros are not significant, all right? So therefore, this has only one significant digit expressed right here, all right? Okay, and then the next rule, again, dealing with a situation where a zero is not significant. If you have zeros at the end of a number and there's no decimal point in that number, then those zeros are not significant, right? And the example here is 50,000. No decimal point indicated, which means that those 4 zeros following the 5 are not significant, all right? So therefore, 50,000 basically has one significant digit, and that's it, all right? So you need to be aware of these rules because they'll become important later on when you're doing calculations and rounding off to the correct number of sig figs. You have to know, in order for you to do that, you have to know the number of significant digits involved in your calculation. And we're going to see how that works shortly. Before I move on, any questions about the rules? Any questions? Any questions? Okay, so let's talk about significant figures when it comes to data and calculation. Now, when it comes to numbers that you're going to encounter in this course or any other, science course, there are two types of numbers, right? You have what are known as measured numbers, which is what we were discussing before. Any number that you get from a measurement, those that's what we're talking about, measured numbers. And then you have what are known as exact numbers. I should have included that here, so I'm right here. Exact numbers. Now, when it comes to exact numbers, there are two types. You have those numbers that are basically defined or come about as a result of definition. So, for example, the relationship between the inch unit and the foot unit, right? We all know that 12 inches is equal to 1 foot, and that is established by definition, right? So the 12 and the 1 in that relationship are exact numbers because those numbers were derived from definition. And then there's the other type of exact numbers, which are known as counting numbers, right? And as the name suggests, basically these numbers are obtained by counting, right? So if you have 12 eggs, right, in a box, that 12 is a counting number, all right? So those are the two type of exact numbers that you will encounter in, any problems. And those are different from measured numbers. One big difference between exact numbers and measured numbers, oh, by the way, here's some other examples of exact numbers. One big difference between exact numbers and measured numbers is that measured numbers have a finite number of significant digits associated with them, and exact numbers have an infinite number of significant digits associated with them. And that also will become important when you're doing certain calculations, especially when it comes to, for example, converting from one unit to the next. And we're going to see some examples of that, all right? So it's very important that you know the difference between measured numbers that are obtained from measurements and exact numbers that are obtained in either two ways, counting or by definition, all right? And you also need to remember that exact numbers have an infinite number of significant digits, while measured numbers have a finite number of significant digits, all right? Now, that's going to be important when it comes to doing calculations, right? So, when it comes to calculations, there are different rules for rounding off your final answer depending on the type of mathematical operation, all right? Now, if the mathematical operation is multiplication or division, then basically what you do is write down or record your answer, or I should say, round off your answer to the lowest number of significant digits of the numbers involved in the calculation, all right? When it comes to addition and subtraction, the rules are a bit different. In that particular case, your final answer must be rounded off according to the lowest number of decimal places of the number or the numbers that are involved in the calculations. And we're going to see some examples of that shortly. In fact, here we go with examples dealing with those rules. All right. So the first example says, for a lab experiment, a teacher wants to divide all of a 453.6 gram sample of sulfur equally among 21 students of her class. How many grams of sulfur would each student receive? We all know how to do that, right? Basically, you're going to divide the mass by the number of students, right? So that you can get the mass for each student. Let me get out of this for the time being. And let me, okay. So it's 453 453.6 grams divided by 21 students. All right? Now, here is where you have to make sure that you understand the difference between the two numbers. The 453.6, that's a measured number, right? The 21 is an exact number, right? So here we have a situation where this has an infinite number of significant figures. And what's the number of significant figures here? 4 significant figures. All right? So if you remember, I said, when you are dividing and or multiplying, you round off your answer according to the numbers involved, which one has the lowest number of sig figs, right? So here we have 4 sig figs in the numerator. We have an infinite number of sig figs in the denominator, which means that whatever answer we get here, we have to round off to 4 significant digits, right? So it's 453.6 divided by 21. And according to my calculation, it's going to be 21.6 that I get on my display. But this is 3 sig figs. You need to express this as 4 sig figs. So what do? We add a 0, right? And that would be grams for each student. All right, and that's it, right? So it's a simple calculation, but in terms of rounding off, you have to pay attention to the type of numbers you're dealing with, the measured numbers as opposed to the exact numbers. And you have to round off accordingly. You have to round off according to the lowest number of significant figures, of the numbers involved in the calculation, all right? And that is true also for multiplication. We just did this for division, but that is also true for multiplication. And I would take it a step further and say that if you even have a combination of multiplication and division, I'm going to just make up an example right here. Let's say, just making up some numbers. So let's say, let's say I gave you this, 2.5 So let's say 2.5 multiplied by 17.38 divided by 50.95, okay? I'm just making up some numbers, right? And let's assume that these are all measured values, right? Now, the correct way to do this calculation, right, is, well, firstly, you have to identify the number of sig figs in each case. So the 2.5 would be 2 sig figs, the 17.38 would be 4 sig figs, and the 50.95 would be, you know what, let me change this to 50.9. Okay, so 50.9 would be 3 sig figs, right? So whatever you get here, when you punch your numbers in the calculator and press equal, whatever you get here must be rounded off to how many sig figs? 2, exactly. So whatever you get here must be rounded off to 2 sig figs. So let me do that. So that's 2.5 times 17.38, and then I divide that by 50.9. And according to what I got on my calculator display, I got 0.8536, blah, 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 blah. I'm going to round that off to 2 sig figs, so that will be 0.85, and that's it, 0.85. All right? So that's basically how you deal with a situation where you have a combination of multiplication and division. You just basically put all the numbers in the calculator and then round off accordingly, right? One common error that students tend to make, and I've seen it up to last semester when some students were doing some calculations. What they would do is that they would multiply this by this and round it off, and then divide that rounded value by this and round it off, right? That's incorrect, right? If you round off at each stage, you might get an answer close to what you should get, but you also run the risk of introducing what we call rounding errors. You see what I'm saying? So when it comes to something like this, you just put everything into your calculator and round off at the end, instead of rounding off at each stage. All right? Okay, let me go back to the PowerPoint. Okay, so that was the first example on that page. Now for the next one, it says, perform the following calculations and round off the answer to the correct number of significant figures. So remember we said that for addition and subtraction, what do? We round off your answer to the lowest number of decimal places, exactly. So in this case, you have to look at the number of decimal places being expressed in each of these numbers that you're adding. So this has 3 decimal places, this has 2 decimal places, and this has 4 decimal places, right? So whatever you get here must be rounded off to what? 2 decimal places. So let's see what this gives. 49.146 plus 72.13 minus 9.1434. Okay, so on my calculator, I got, and please correct me if I'm wrong. If I made any mistake, please don't hesitate to let me know. But I got 112.1326, right? But now we need to round this out to 2 decimal places. So what would be the final answer?
112.13.
Exactly, 112.13 meters. Don't forget the units, meters, all right? And that's it. That's how you deal with addition and subtraction, right? Now, and I wish I had an example of this, but there's another question that arises, and that is, okay, what if you're dealing with a situation where you're doing, let's say, addition followed by addition followed by multiplication, right? Because you know the rules for rounding off for multiplication is different from that for addition, right? For multiplication, it's the sig figs that you look at. For addition, it's the decimal places. So what if there's a combination of those types of operations? How do you deal with that? So again, I'm going to make up an example to illustrate how to deal with that kind of situation. So let me go back to this right here, and let me so let's say you are given something like 3.7 3.75 minus 2.55 and then multiply by 3.49. Okay, just making up something here, all right? So how do we round off correctly in this particular case, all right? So in the numerator part of this expression right here, you have a subtraction taking place, right? So the rules for rounding off when you're subtracting is that you round off according to the lowest number of decimal places, right? So basically 3.75 minus 2.55 give you 1.2, and we have to add a 0 here, right? Divided by 3.49, okay? So we have to round off to the correct number of decimal places, which in this case would be 2 decimal places, all right? And then now we do the division, right? And of course, the rule for division is you round off according to the lowest number of significant digits, right? So in this case, it just so happens that this is 3 sig figs, and that is expressed to 3 sig figs. So your final answer when you do that division would be rounded out to 3 sig figs. So that's 1.20 divided by 3.49. And according to my calculator, I got 0.344. Because I got 0.343839, some other digits. So when that's rounded off to 3 sig figs, that's 0.344, all right? So if you have a combination situation where you have, you know, let's say addition or subtraction at one stage, and then a subsequent calculation step would be a division or multiplication, that's when you do the rounding off at each stage. You see what I'm saying? So you do the subtraction, you round off according to the rules for subtraction, and then when you do the next step, which is the division, you round off according to the lowest number of sig figs, which would be the rules for division, right? So that's basically how that is done. Okay, any questions? Any questions about this? Okay, let me go back to the PowerPoint. And let's see what's next. Okay, so let's talk about conversion factors, right? Again, this is something you should have met before in your introductory or high school chemistry, because we know that we have different units for the same type of measurements. For one, you have the metric versus non-metric, and even within the systems, you have different relationships. For example, in the case of non-metric, when it comes to mass, you have the relationship between the pound unit and the ounces unit, for example. We all know that 16 ounces is equal to 1 pound. You have the relationship between the inch unit and foot unit, 12 inches is equal to 1 foot, and so on and so forth. And then on the metric side, it's easier because, of course, they differ by factors of 10. So you can have the relationship between kilogram and gram, millimeters and meters, and so on and so forth, all right? So what we'll be looking at here in this section is how do we convert from one unit to another, right? So basically, there are several methods that can be used. The one that we're going to look at here is what is called the unit conversion or conversion factor method. And basically, the first assumption that we're going to work off, which we all know to be true, is that multiplying any quantity by 1 does not change the quantity, right? The same quantity or unit in both the numerator and denominator of a fraction will cancel when carrying out these type of calculations, right? So I think I told you before that I have in that packet, in one of the pages, it gives you the relationship between different units. So it's a lot that which is provided in Canvas is a much more comprehensive list than the one that we have right here, right? So basically, we're going to look at the relationship between the inch unit and the centimeter unit, right? 1 inch is equal to 2.54 centimeters, all right? And please note it has a star here, which basically indicates that the US inch is defined exactly as 2.54 centimeters. So that's an exact relationship. The relationship between the inch unit and the centimeter unit is an exact relationship. So what that means is that the 1 and the 2.54 has an infinite number of significant digits, all right? Now, so therefore we can use that relationship to convert from the inch unit to the centimeter value and vice versa. And I think the example, well, before we get to the example, so basically when it comes to the conversion factor that we'll use to represent this relationship, there are two possibilities. You can have this or you can have this, all right? And the one that you're going to use is dependent on the type of conversion that you're trying to carry out. You would use this one if you want to convert from inches to centimeters. You would use this one if you want to convert from centimeters to inches, all right? And let me see here. Okay, I thought I had the example here. But basically, the one that you're going to choose is based on the answer to this question right here. And basically, you're going to use the one that will cancel out the unit that we want to get rid of and introduce the unit that we need, all right? So, okay, here's the example. So this question says, what is the length in millimeters of a 1.25 foot rod? So let me get out of this again and go back to this. So basically in this question, you're given the length expressed as 1.25 feet. And the question is asking for the equivalent values in millimeters, all right? Now, in most tables, for example, the one that I provided in Canvas, you will not see a direct relationship between the foot unit and the millimeter unit, right? You won't see that, all right? But you can establish relationships between some intervening units, right? So I'm looking at this here. So the question I have to ask myself is, how do I get from the foot unit to the millimeter unit? Well, I know that 1 inch is equal to 12 inches is equal to 1 foot, right? I also know that 1 inch is equal to 2.54 centimeters, right? I also know that 100 centimeters is equal to 1 meter. And I also know that 1000 millimeters is also equal to 1 meter, all right? So based on what I have here, what I can do is convert from foot to inches, and then from inches to centimeters, and then from centimeters to meters, and then from meters to millimeters, all right? So basically, I'm going to need to convert, I'm going to need to use 1, 2, 3, 4 conversion factors to achieve the final answer. So I'm going to start off with what we're given. We're given 1.25 feet. And the first thing I'm going to do is convert that to inches. And the way I'm going to do that is that I'm going to multiply by this conversion factor, where I'm going to put 12 inches above and 1 foot down here as a denominator. So this conversion factor is representing this relationship right here, all right? As a result of this, and the reason why I set this up like this is because I want to cancel out the feet unit, all right? So we're up to this point, we're left with inches, all right? So now we're going to try to go from inches to centimeters, right? And therefore, we're going to use this relationship here. So how are we going to set that up? Above, we're going to put 2.54 centimeters, and below, we're going to put 1 inch, all right? And as a result, the inch units will cancel out, and now you're left with the centimeter unit. But we're not finished yet because now we need to go from centimeters to meters. The relationship between centimeters and meters is 100 centimeters equal to 1 meter. So I'm going to put it down here. I'm going to put 100 centimeters down here as the denominator and 1 meter up here as the numerator, so that this centimeter unit will cancel out with that centimeter unit, all right? And then now, to get from meters to millimeters, we're now going to use this relationship, right? So down here, I'm going to put 1 meter, and above, I'm going to put 1,000 millimeters. And by the way, this should be millimeters here, right? So this will cancel out with that, and that's it, right? So now we have to do the number crunching. But before we do that, we need to make sure that we know what type of numbers we're dealing with, right? In other words, exact numbers versus measured numbers. The 1.25 feet here is obviously measured, right? And it has 3 sig figs associated with it, right? This here is an exact relationship, right? So that has an infinite number of sig figs. All right? The same is true for this relationship right here. That's also infinite in terms of sig figs. The same is true for this one. Infinite. Is that my phone? And then last one here is also a defined relationship. So that also has an infinite number of sig figs. All right? So basically, what does that mean? That means that whatever you calculate here at the end of all of this, you have to round it off to 3 sig figs, right? So let's do that. So it's 1.25 times 12 times 2.54 divided by 100 multiplied by 1,000. And according to my calculator, I got 381, which is 3 sig figs by itself. And the units here would be millimeters. Yes, ma'am.
Would that 1,000 be on the bottom with the 100, or would that be on top?
On top. Because 1,000 millimeters is equal to 1 meter. Yes, so that is correct. All right. Okay, any other questions about this one? Any other questions? So that's basically how you carry out conversions, right? Basically, you have to figure out how to get from the given value to what the question is asking for, right? And you may be given a question where there's only one conversion factor that you can use, or that that will be used because there's a direct relationship. But as you can see in this case, you might not have any charts or tables that will give you the direct relationship between the initial value unit and the final value unit, all right? Okay, so if there are no questions on this, let me go back to the PowerPoint and see. Okay, so the next question is saying, what is the volume in cubic centimeters of the block of wood pictured here, all right? So they gave you this block of wood, And the dimensions 4.41 by 4.13 by 7.36. So let me go back to this right here. And let me okay, so let me write down these values here. So it's 4.41 inches by 4.13 inches by 7.36 inches. All right. So the question is asking for the volume in, centimeters cubed. Okay, so the way I would do this is I would ask myself, what's the relationship between inch and centimeters? And we know that 1 inch is equal to 2.54 centimeters, right? Now, if you want to get from inches cubed to centimeters cubed, that means you have to cube both sides, right? And what I would do is multiply this here by a conversion factor which represents that relationship. So I'd multiply this by 1 inch cube here and 2.54 centimeters up top, and then cube it, all right? And then we work this out. So 4.41 times 9.13 times 7.36 multiplied by 2.54 cube. And again, we have to round off to 3 sig figs because these are measured values. These are each 3 sig figs. This is exact. So according to my calculation, this works out to be 4.86 times 10 to the 3 or 4860. And the units here would be centimeters cube. And that's how.
Did you put a 9 in the second one, or did you say 4
Where?
in this, on the top equation and then
You
4?
mean here?
Yeah,
No, that's 3. That's cube. Let me see here. Right, okay. And that's it. All right. Any questions about this one? Any questions? All right, so those are just 2 examples of how you actually carry out unit conversions. All right. Okay, so going back to the PowerPoint. Oh, another example. Now, this question has to do with something, a measurement that is used in health sciences, the body mass index, which is, I guess, one of those measures of health, basically. So basically, the question says that the definition of the units of the body mass index is this right here. So that implies to get the value of the BMI, you take the mass of the person and divide it by their height squared. All right? And the question says, or a question continues to say that if the BMI exceeds 25, then the person is considered to be overweight. So the question is asking, what is the BMI of a person who is 69.0 inches tall and weighs 158 pounds? So the way I go about doing this is that I would take the 69.0 inches and divide it by 158 pounds, right? But what I would do now, once I get that fraction set up, is that I would concentrate on converting each of these units to the required units. So in the case of inches, actually it should be the other way around, my bad. It should be 158 pounds divided by 69.0 inches. All right. So I was saying that what I would do in order to carry out this calculation is focus on converting each of these units to the required units. So I would focus on converting the pound units to kilograms, and then focus converting the inches unit to meters, right? And in fact, there's another correction I need to make here. This should be squared. So that means that I would have to focus on converting from inches squared to meters squared, all right? So let's see how we can do that. Now, what I'm going to do is focus on converting from pounds to kilograms, right? And now I don't know or don't remember what the relationship is between the pound unit and the kilogram unit. Let me see if I can find the table. Tables. Okay, so this is the table. And remember, you'll have access to this table while you're doing your tests. Or exams. So you don't need to memorize stuff and you don't need to print your copy. I'll provide it for you. Okay, so let me scroll down to the conversion factors. Okay, so the relationship between pound and kilograms. Okay, so that's relationship here. 1 kilogram is equal to 2.2046. So down here, I'm going to put 2.2046 pounds, and that would be equal to 1 kilogram. So that the pound units will cancel out here and here, right? Then I will focus now on converting inches squared to meters squared. So I'm going to put 1 inch here and 2.54 centimeters here. And don't forget to square that. All right. So that the inch squared unit will cancel out with this inch squared unit here. And then the next conversion factor is where I convert the centimeters to meters. 100 centimeters is equal to 1 meter. And again, can't forget to square that, right? So that the centimeter unit squared will cancel out with the centimeter squared unit. All right. And then we do the calculation. So the final units, by the way, in your answer would be kilogram per meter squared, which is basically what is required there. So let's do the number crunching. 158 divided by 69.0 divided by 2.2046 divided by 2.54 squared. Where's my squared thing? Okay. And then multiplied by 100 squared. Okay, so I did something wrong. This is too large. Let me do this again. 158 divided by, I forgot to square the 69 squared. Okay, I should get it right now. Divided by 2.2046 divided by 2.54 squared multiplied by 100 squared. Okay, that's more like it. So the answer I got, and please correct me if I'm wrong, if you got something else, but I got, now how many sig figs do I need to roll this off? 3. So 23.3 is the answer I got. All right. Any questions about this? Questions? Any questions? Okay, and I think that is, there's one more topic in this chapter, and that is density. And I'm quite sure we're all familiar with what density is by definition, right? Density is, by definition, the mass per unit volume of a substance. And it's a very simple formula that you can use to calculate the density. D, the density is equal to mass divided by the volume. And therefore, as a result of that, the unit of density is dependent on what units you use for mass and volume in that equation, right? Typically, when it comes to solids and liquids, the density is expressed in grams per mil or grams per cm cube, which is the same thing, right? So for example, ethanol, the example given here, has a density of 0.791 grams per mil. And it turns out that we can actually use the density and express it as a conversion factor for the purposes of doing certain calculations, right? So in the case of ethanol, we can express the density as this conversion factor, 0.791 divided by 1 mil, or this conversion factor, 1 mil over 0.791 grams, right? And again, which one you would use is dependent on the type of calculation that you're trying to accomplish. So I would use the first one if you're trying to find the mass and you're given the volume. I would use the second one if you're given the mass and you're trying to find the volume. So it all depends, all right? And I think we have some examples here. Okay, so this question here says a beaker has a mass of 85.2 grams when empty and 342.4 grams when it contains 325 mils of liquid methanol. What is the density of the methanol? So basically what I would do is first try to find out the mass of the ethanol. Let me do that down here. So the mass of the methanol is equal to the difference between 342.4 grams minus 85.2 grams. So when I do that calculation, 342.4 minus 85.2, and I got 257.2 grams, all right? So that's a mass. So to find the density now, that will be equal to the mass divided by the volume. We just calculated the mass, which is, oh, wait a minute. Decimal point here. Okay, so in the case of the mass of the methanol, that's 257.2 grams divided by the volume. What's the volume? The volume is 325 mils. All right, so let's do that calculation. So 257.2 divided by 325, and according to my calculations, this works out to be equal to 0.791 grams, and please know the unit is grams per milliliters. All right, and that's how you do that. Okay. Any questions about this one? Any questions? Any questions? Okay, the next one is asking for the mass of methanol in kilograms that it will take to fill a 15.5 gallon fuel tank of an automobile modified to run on methanol. Okay, so let me clear this here. Okay, so basically what it comes down to is this. They gave you 55.5 gallons and they're asking for the amount of mass in kilograms associated with it, right? Now, the way I would go about doing this is that I would try to find some way of converting the gallons to mils, right? So you're gonna need this table again. Oh, and there's one person joining us by Zoom. Okay. Let me close this off. Let me minimize this. Okay, so this is what we're going to look at. We want to convert from gallons to mils. So let's see. Okay. Trying to fit both on the same screen. Okay, so, to get from gallons to centimeters cube, I could use 1 gallon is equal to 3.7854 liters. So 1 gallon is equal to 3.578? $3.7854. $3.7854 liters, all right? So we can go from gallons to liters. We can go from liters to milliliters because 1,000 milliliters is equal to 1 liter, all right? So basically, I'm going to take the 15.5 gallons, multiply it by, down here, I'm going to put 1 gallon, and up here, I'm going to put 3.7854 liters. And then the next conversion factor is going from liters to milliliters, right? So 1 liter down here, 1,000 milliliters above, right? So the gallons will cancel out, the liters will cancel out. Now the next conversion factor would be the density, right? And we calculated the density already to be equal to 0.791 grams per milliliters, right? So the milliliter units will cancel out here and here, whoops, and here. But we're not finished yet because the question is asking for the mass in kilograms. So there's another conversion factor that's needed where we convert from grams to kilograms, and that would be 1,000 grams below and 1 kilogram above. So that goes with that. And then we do the number crunching, 15.5 times 3.7854 times 1,000 times 0.791, and then divide by 1,000. So according to my calculations, now in this case, we have to round off to 3 sig figs. So according to my calculation, that would be 46.4. And the units here would be kilogram. And that's it. That's how that calculation is done. All right? Any questions about this? Okay. So let's see here. That's it for chapter 1. So now you're going to get to do your first assignment. All right. It's all based on chapter 1. I'm going to pass down. That's for you. And you want to pass down. And for the sole person that's out there in Zoom, don't feel left out because what I'm going to do is publish the same assignment that I've handed out to the students here. Here. Okay, so files, assignment. Okay, so for you out there, Addison, out there in Zoom, I'm publishing assignment number 1 right now. So you should be able to click on that link and download it. And get started on it, all right? So, yeah, go ahead and start it. If you have any questions, feel free to ask. I'll be right back. Did anybody? Well, I know one person joined us online. Addison Sneller. Did anybody else come in late? No?
I don't think you called my name when you did attendance though.
What's your name?
You're the one.
Oliver? Oh, okay. Yeah, I did call you.
Oh.
By the side. It's not that hard.
That's a nice
Yes,
list.
sir.
For the definitions, do you want the definition specifically from the slides, or do you want us to change it to our own words?
I will do,
Do whatever?
as long as the meaning conveyed is the same.
Okay.
Mhm.
Milligrams in here, because there's no conversion for any gram to milligram.
Good question.
Number 2 on page 3.
Yeah, milligrams, yeah. 1,000 milligrams is equal to 1 gram.
Oh.
Mm. Remember, milli means 1,000th, right? So that means that 1,000th of a gram would be a milligram, so that means that 1,000 milligrams equal to 1 gram. Sorry.
Almost in the right order of how they are to be.
No, it doesn't have to be in a particular order as long as the units cancel out. That should be canceled out. I think you have chosen a more difficult. Because you can go from kilograms to grams and then from grams to milligrams. You know what I'm saying? Kilo means 1,000, so. Something like that. No, I need paper. Oh, okay. So in this case. We start off with 2.0 times 10 to the 36 kilograms. What I will do is multiply this by 1 kilogram, 1,000 grams. So that goes with that. And then I'll go from grams to milligrams by this.
Oh, okay, thank you.
I mean, you probably will get the right answer doing that way, but that seems to be a bit more difficult way of doing it as opposed to that. Yeah, thank you, Ben.
Thank you.
Okay, it's now 11:50. So I'm going to give you some time to complete that assignment. What I'm going to do is I'm going to open up the Dropbox that you can okay, so let me do this. Let me set some deadlines here. Okay, so today's the 14th. I'm going to set the deadline as the 17th for you to submit your assignment. I'm going to give some instructions as to how to submit it because based on past experience, I've had some issues. So it's going to be available from today until the 17th. Okay, so it's set up. One of the things that I'm going to leave in the instructions is that you have to make sure that you save your assignment as a PDF document and upload it into this Dropbox I've just created, all right? Well, see you on Monday. Oh, and I'm gonna see some of you in the lab, right? So, yes, sir.
You know, yeah.
Yeah.
This school, is chemistry, he has the online version. And he wants to know if you will allow him in your lab.
Can't do that.
It's full.
It's full, 24
Yeah,
students and there are safety reasons really.
No, I told him he wanted me to come and ask. I told him I'd come and ask. Listen, I was a teacher.
Oh,
I
okay.
taught science in high school. I taught mostly biology.
Oh, okay.
So I told you, but I told him I would come and ask.
Yeah,
Did anybody drop your class?
well, that's the thing now, because then, like one student that was just here, he told me that he just waited and kept checking the class, and somebody dropped out and he just went right in. He just registered. So I don't know if they still allow that at this time.
I
But
think what's going on, he's a transient student, so.
right.
Like, they don't let transient students just add the class.
Oh, okay.
Like, but here's another question, is there a way that, what I did, I run a AIDS for person disability company.
Okay.
And so for, he was doing some studying, like he had some research hours, he's trying to get a med school and all that. And so for his internship, I did hire him, we're gonna hire him for the summer full time. So I was wondering, is there a way that could he work for you? Could he do something in that, do you need an assistant or something?
Wow.
Cause he's very, he can be he's very helpful out here.
I'd have to see what the college, what the college policies would be on something like that, because he's not a student here.
He does have the chem class. He has the chem class completely online here.
Oh, so that's the lecture, Chem one?
Yeah, he has the lecture, but he doesn't.
Have the lab,
Exactly.
okay.
And that's what's gonna require the
Yeah,
lab.
the lab as well as the lecture, yeah.
Yeah, so coming back from Sarasota now, because new college, you know, it's the honor college of. Here, first of all, here's Dr. Nicely. First off, so say hi to him. He did say his lab is full, but I just want you to say, you know, what's up to him and all that.
Yeah, I was telling him that, you know, for safety reasons, the lab is capped at 24. So it's full right now. So that's, in fact, I'm going to the lab, shortly, right now.
But I did ask maybe if there's a way, like, if you could be, because he has plenty of, you know, he's a junior,
Right,
so he got plenty of like other science. He could be like maybe like a lab assistant or his assistant or something like that. And he said he's gonna look into what the college was.
yeah, I have to see what the college has to say about that. I've never heard of that being done here before.
Yeah.
So I'll have to look into that.
It really happened where you at. And
Oh, at the new college, at the new,
yeah, because he goes like the honor college of,
oh, okay,
like, what you're doing your research on?
Athletics, it's electromagnetic waving.
that sounds like physics.
Yeah, it's
Psychology, yeah, physics, psychology,
Oh, okay,
you know, especially with the.
yeah, I'll have to look into that.
Okay,
But,
no problem, but I appreciate your time.
yeah, no problem, no
I
problem.
remember.
I mean, trust me, you're not the only one. Everybody has been asking me to